turn the AC off if it's okay for everybody, and we will open the windows because it's windy enough. Okay, so we are at Facebook and YouTube, so you can start. Welcome.
Hello. Yeah, let me get the volume right on this. So I chose a talk title that is meant to look like one of these viral commercial kind of things. You know, all you need, the one simple trick to getting clean teeth, you know. And to me, over the last 20 years, it really feels like a lot of AI hype has used exactly that kind of formula. There's been a large set of the all you need kind of prescriptions, and they're usually not really the right thing. So what I'm going to try to do today is just focus on what are the problems of AI? How do we make sure we understand the core problems? And then look at how the gap between the core problem that we really are trying to solve and the methods we're using reveal why certain behavior in AI that bothers everyone and it seems hard to fix is there. And I'm not going to provide you with solutions to everything. This is about finding the problems, right? To get a really good problem description. So I think the biggest danger of AI is exactly this cartoon. Increasingly, people will just not want to know anything because they can just, you know, say, "Hey, Chat GPT, what should I do today?" Okay, so I'm also trying to play off a little bit of complexity science here, because a lot of this behavior on the part of the research community isn't necessarily the research community. It's the way it's translated in the news. We all know that, right? But most of these things are all statements made by the research community. So it's not entirely, you know, bad for me to point this out. So reductive oversimplifications. So if we reduce complexity, then, you know, we're not going to have a complex system anymore. And some of these have cost us deeply. We'll talk a little bit about this. So the first thing on the far right is about 15 years ago, there was a huge hype that data is all we need. So that's the first thing. It's not really the case that data is all we need. Of course, we need freaking data, you know, but is it the only thing we need? Okay. Reward is enough. For those of you that don't realize that every chatbot is a particular kind of artificial intelligence agent called a reinforcement learning agent, reinforcement learning agents all use reward signals that are handcrafted by engineers. And it's not enough. But a bunch of researchers really thought that it's going to do everything. Perception, planning, motor control, knowledge, common sense, imagination, social intelligence, even language can all come out of a single scalar quantity that's designed by engineers. Yeah, attention is all you need. That's, you know, we're still living in that era, right? Okay. So what I'm going to try to do in the talk is articulate the problems of AI and their current formulations, and then try to show you that there are real problems induced by decoupling AI systems from real systems. So by decoupling, I mean, when I did a lot of my earlier research in robotics and computer vision, the whole goal was to keep the system in the loop constantly. One of my first projects as an assistant professor was to replicate these MIT studies of the ping pong robot. You know, it's like real time, in the loop kind of stuff. Can I, you know, anyway, that was fun. People are still doing that research, but it is not the most important research. It's really like fringe at this point. And some of those problems are still notoriously hard. Like, how do you get robots to grasp? I worked on that. That was what I did 2003 and 2004. That was a long time ago, and it's really not that much better. So here's my list. So this is the whole talk. This is the takeaway. You really can leave after reading this thing. Reductive data practices have led the inability to ensure the truth of claims, distinguish validity. They ensure that the systems that we are training on current data lack coherence and closure, and there will be problems with understanding and interpretation. And I will define exactly what I mean by understanding and interpretation. That will be a very minuscule fraction of the human range of understandings of understanding. So second thing is that systems are resource decoupled. And there's a number of things about this that are weird, but just one thing, just to point out, even though the current AI systems we have, we believe that they're so much faster than us at computing. That's true, but they are literally 10 to the 6 less efficient energetically than humans. Huh. So we are way better at being efficient about resource usage. Why would that be? Well, we're coupled to the world where if we don't use our resources well, we're gonna not do well. Right now, these are like little babies. We give them all the resources they'd ever need, right? Yeah, and they're not nice babies either. So as the resource decoupled, there's really direct consequences of that. They're not interacting with real things. Without interacting with real things, then they're going to not end up having the ability to learn from constraints about what it is that my own purposes might be, and so on and so forth. But I'll also just put out that I really think there's a core lack of innovation that will emerge from the dictum that necessity is the mother of invention. There's no necessity right now. Second thing is really just the community. There are problems that are induced by strong pre-commitments to very restrictive computational methods and models. And those pre-commitments are ones that are making the current computational systems incredibly costly and scale poorly and require centralization, because the whole paradigm is centralized. And I think it's actually that way on purpose at this point, because the number of people that are working on decentralized versions is minuscule. So there's got to be something about that too. Anyway, so this is what we're currently doing. I'll explain this a little bit more, but an LLM is going to parse a language sentence. It does that parsing by unrolling all of the parse tree. What does that mean? If you don't know, if you're not a computer scientist, that might make a lot of sense. But in computer science, we do a lot of things by recursion. We'll put it in the loop and we'll recurse. To actually explicitly unroll something means that we do a multi-step process, not by saying, hey, you could take the next step and then the next step and then the next step and just take the next step when it's needed. No, you explicitly detail every plan. So it would be like me telling you guys how to walk step by step, not just across this room, no, for the rest of your life, every footfall, and we're going to encode it in the weights of a neural network. So unrolling something is an incredibly memory expensive way of computing, and that it doesn't have to, neural networks don't have to work this way either. So that we have unrolled parse recursion, and then we're using, this forms a tree of possible parses, and then we use RL to find the shortest reward augmented path where the reward signal is coming from what you guys like. And so what's wrong with this? Well, it's not necessarily that there's anything intrinsically wrong with it, but it's not solving the problems that were posed for it to solve. And so now let's look at if we can get something out of some additional tools. So what is AI trying to do right now? Pretty much everything that humans find hard. If humans find it hard, we hope we can throw AI at it, and that it will become easier, right? The AI landscape right now is one in which we have almost everything that we could potentially get data on, and we're trying to throw AI at it. And increasingly, we're doing it from this agentic point of view. So an agentic point of view just means that we're trying to provide some autonomy to the AI system so that it gets to make its own actions and choices and so on and so forth. And we're discovering that we have to embed in these systems more and more knowledge type structures. So profile, memory, planning, action, these additional things that are getting added are all essential efforts to try to provide data needed to make data friendly the things that humans do. That said, the actual systems, the way they work, is exactly still just a large unrolled data lookup tree, the parse tree lookup, together with a RL system. And the RL system, even when it's doing thinking, is actually in this little chain right here. It's actually still just doing a simple look ahead, recurse, look ahead, recurse, in which every step it's just trying to see if the path that it's on right now is a good path. That's not really thinking in the same way that you and I think about thinking. And this is universal. I mean, there are no thinking machines in this paradigm. That doesn't mean that AI hasn't made thinking machines. There's a ton. It's just not in this family of models. So here's the family of models that everyone's really using a lot. We have, as a knowledge base, a token transformer. What are tokens? Tokens are taking data and turning it to a discrete form, a discrete sequence, and then allowing yourself to transform that, is why it's called a transformer, from one token set to another. And you memorize all the transformation paths. It memorizes all of the transformation paths. I could say that over and over again, but it's unrolled all the transformation paths. They're explicitly represented. There's almost nothing implicit there. And then that the agent is acting over the possible transformation paths as its state, taking in reward. And so its environment is the LLM. And its actions are, do I continue to query or add a little bit? Do I continue to work off of the output of this system? Okay, so what does ML or machine learning in general do to solve problems? So ML in general to solve problems does what I'm putting in here, ideally. And as a standardized equation, I'm hoping that this is big enough that it covers all of the things that we're hoping that the LLM would do. So it's notation heavy, but we have an objective function that you minimize. All machine learning, all AI that's learned from data uses this kind of an explicit functional in which we try to embed something that would produce probabilities as a target. And in that embedding, we use different kinds of data in order to try to regularize it. The most difficult kind of data in general is the one in this red box here. What we've tried to do is take all of the red box kind of things, experiences that you might have from interacting with an actual world, and replace that with textbook learning. So textbook learning is supposed to replace real life for LLMs and potentially for you guys now too, because you're going to design your lives around what an LLM outputs. So the second term right here is the traditional divergence term from training data, and the last term is just basically what you can't get right. So that equation is used by that entire system. An LLM is trained according to that equation. The RL agent is trained according to that equation. And there's basically two families of problems that these two major components were intended to solve. So the LLM itself is something called the domain model. Domain models, what they're supposed to do is allow yourself the ability to take a large set of interrelated data and make any query that you want on it. So they're called domain models because of that. So a domain model means that it's not a single query machine. So as an LLM, you give it data, but the data comes in the form of values that are paired. It always comes in this form. And that pairing happens exactly during the data set creation. So for instance, to train a chatbot that can do question answering, we create a data set that has some questions and the corresponding answers. That's this pairing. Once you have those correspondences paired in your data set, that pairing acts as what the machine learns. It learns from the pairing. And so the problem then is to find data mappings that preserve the correspondences that you put into the data set. So you can do search this way, query data goes to response data, you can do recognition this way, instances go to a description of the instance, which can go to a class of classification. You can do generative AI, which is to invert the recognition process, for instance, and do description to instance. You can do forecasting. You can take current data and try to project it into future data. You can do translation, which is to take data encoded in a certain way, like English, and try and translate it into a different form, like Akkadian. In this current solution approach, the methodology is to use flexible function families, aka deep neural networks, parameterized by big weight matrices, and optimization. You optimize the big objective that I showed you in the previous slide, coming up with optimal weights, theta star. And ideally, that will preserve the correspondences. This backward arrow is on purpose where this R relation, this R means that the correspondences you put in, like question corresponds to answer, is a relation that you wanted. You're like, yeah, this was the right answer to that question. So these are related. So this is a valid thing. So you want all of those valid relational things to be embedded in a way that if I only gave you one part of the data, the machine would give you the good match correspondence for free. Now, this whole problem, though, raises a set of meta problems. How do we make our data sets? Because everything boils down to the data set now. So we're going to really try to reflect on this carefully. Data correspondences now must reflect everything faithfully into the data, everything that you want. So if there are domain constraints, if there are extra task criteria, if the data actually has hidden context and you forgot to label the data by the context, oops, then it may be that task solutions, the correspondences, will not actually work correctly because it wasn't in the data. And the machine is just doing what it told you, what you told it to do. It's like, yeah, I found it. So what's the other big family of AI problems? So if you have a domain with a lot of correspondence data and you also have processes that operate on it, and those processes have to be stepwise, one step at a time. So these are all the preconditions. Then if you're given data in the form of this correspondences together with some actions, then you can look at how the correspondences hold in the context of the actions. So maybe the action is something that's like causally changes the way things work. So, well, at least you've recorded the action now, so you have some more context. But then there's one other thing that's given for all of these executable steps so that we can make an agent that does things, not just says, oh yeah, I understand what's happening. No, we want it to do things. And so we augment what it does by giving it a reward function. The reward function is a real valued signal that orders the observed values over the steps. So it's always that, I'm being very specific because that's what the reward function must do. It must order the A values so that some A values are higher than other. That's what it has to do to be a good reward function. So how do you make those reward functions? It's freaking hard. It's not easy. It's really not, requires enormous cleverness. And when you don't do it well, freaking disaster. So the overall problem now, though, is that you can optimize traversals stepwise, little steps of what you want to do with respect to local observables. And this fits into the computer scientist's dream, making a greedy algorithm. Greedy algorithms are ones in which you feed it just one piece of data and it just knows what to do. If you feed it another piece of data, it knows what to do, right? So that's what we want to do. That's the structure of RL models. The current solution approach is the same as before, flexible function families, but add a particular kind of optimization method that's really good at doing these stepwise optimizations, one little step at a time, called dynamic programming. So the problem then formally is that you want to learn an embedding, and the embedding is a new function that tries to take a list of all of these values of the data and do something kind of like the LLM is doing. So the RL agent is making a kind of a weird copy of what the LLM has in it as well, because it's trying to embed in it the histories of what comes out of the LLM. And then it learns a policy, which is a plan for how to act so that it can take the embedded value and just look up an answer. And the meta problems for this are you have to encode domain constraints. The reward function must reflect all object, blah, 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 blah. And the embedding must cover all futures. This embedding problem is really theoretically interesting and hard, but there's an implicit stationarity into this very approach. It shows up immediately when you're looking at it. And so again, my answer to this question about can we use this for adaptive studies? Are these agents adaptive? This particular piece of these agents is limiting the ability for it to be adaptive, because that once it learns a function of how to embed histories into a value, it's taken a huge amount of history to do that. One tiny little thing won't cause an adaptation anymore, right? Okay. Okay, so what kind of knowledge do LLMs have in general? Well, what is knowledge? Yeah. So we classify knowledge on the basis of how we use it, right? So structural knowledge is a relationship between objects and concepts. What a concept, I agree with our last speaker. Some of these things are hard. You just decide that, yeah, you feel really dumb after a while because you're just defining everything in terms of everything else. But declarative, active knowledge, it's declarative. It means things like, I tripped over this chair, whoop. So it was active. You would have knowledge that I did it. That's easy. So this part is really pretty basic. I dropped this thing and it broke, Heuristic knowledge are rules of thumb. Most of the time something happens this way. Meta knowledge, knowledge about knowledge. What's the grammar of a language? Procedural knowledge. This is where we spend most of our time in the modern world. The people that rule the modern world prefer us not to have any real knowledge. What's real knowledge? I don't know. But procedural knowledge is just really, really heavily weighted. Do you know how to do something? Can you do it? Let's do this. It's like, don't ask why, ask how. That's the modern era. These guys would have disagreed, right? So how do we represent knowledge? As an accessible memory structure, representable as incidences. So incidence is a technical term. It means that I have two different kinds of objects and I can put them into a correspondence. Oh, it's a correspondence, yeah. So how do humans update knowledge, impute likely facts, and do guesswork? These are all the things that we do regularly. And can modern AI do those things? This little list right here, those are the hard problems. So as a knowledge representation, we have tons of things that are represented as graphs. We have large language models sitting and consuming all of this structured data. LLMs have now consumed everything. I could just say that word over and over again. This was sad. But there's all of these projects. Some of them, they took humans, really smart humans, 40 years now, just. So Where's it gone? It's just gone into a weight matrix that's unrolled all paths of conversion between this and something else. So adding knowledge, because knowledge is kind of a memory structure, very often just means that we're adding different kinds of storage or extra data. We're augmenting our data representations. And as we augment our data representations, lo and behold, we get things that look more and more like the kinds of memories that humans have. And when AI researchers started just taking the human style memory breakdown and building it into game agents started kicking ass. So it was a big deal. But what does it mean to represent knowledge? Are LLMs knowledge representations per se? I think this is really hard, but there are some things that we can make extremely specific conclusions about. And that's LLMs were by design, by design, I mean, solving the problem that they're intended to solve means that there are things that they cannot easily do. And it shows up when you test them well. So here's a person, here's the response, who is this? There's all of these things that are incorrect or made up. And we're all used to at this point thinking that this is just the random seed part. But the bigger deal is that all of the data that went into the training process is, by the nature of the way the optimization works, must be presumed to be valid. There is no ability for the training procedures we use right now to distinguish between invalid and valid data. It is impossible for it to do that. Unless we change the way we train our agents, we will not have agents that we can train on invalid data. Our data must be carefully curated, and increasingly AI agents are being trained on their own outputs. And an agent, an LLM that has been trained for a billion cycles on valid data collapses after 35 training iterations on its own output. That's crazy. So there's a paradox of learning to reason from data. And learning to reason from data, one of the things that we do well is that we can do something called go from a proposition to a preposition. So a proposition means that you have a fact, concrete fact, but what I'd like to do is generalize it in some way. So let's go backwards. Socrates, who's this Greek guy, he was a man and he died. That's a concrete fact. He's dead now. Pretty sure. But we can lift this to the famous dictum, all men are mortal. Socrates was a man, so Socrates is mortal. That lift isn't necessarily true, but it's an example of this lift from a concrete to the abstract, a preposition. So one of the interesting things is if you carefully look at how an LLM agent can learn from a logic problem database in which there are logic variables in which the problems can take on both true and false for the same variables. Does that make sense now? So there's multiple instances of each problem. Sometimes the variable in the correct solution would be true, sometimes it's false. You can give the entire corpus of problems to the LLM agent and it cannot memorize them, which is actually a good thing. That is great, because that will attack one of the other things. But it simply cannot learn them all. So this is exactly where it breaks, this problem of going to variables. So when you're careful about testing, the problems start emerging for what it is that they can do. And the issue here is that LLMs, by doing this loop unrolling, they only have the paths available to them that would be taken. And if a path overlaps too much, it will destructively interfere, because these are all concrete paths. There are no variables in the system. Without variables, it can't represent the idea that I could do something up to a free value. There's no free values in a LLM. So people that are working on neurosymbolic AI, they want to add values back. There are really important problems that require you to have free values in order to solve. So why am I talking about category theory? So what is category theory, blah, blah, blah? Well, it's math for people that really, really like math and don't really like other people. And I kind of fit that model pretty well. So the origin of category theory was really trying to figure out how to make sense of a bunch of weird correspondences between logic and topology. Why did these correspondences exist at all? So let's try to lift up exactly this preposition thing, lift up to the point that we can see the fact that they're all related if we remove some of the details. So categories you can think of as collections of objects, potentially with internal structure. So my favorite way of thinking of a category is as if it's a cell in a body. Like a cell has a lot of complicated machinery, right? But it has a boundary, so it's still a thing. That's a object in a category. Cells also interact with each other, right? And they often interact in a way that they maintain closure. If the cells in your body stopped interacting with each other, what would happen to you? You'd melt. That would be bad. Don't do it. So closure means that these interactions have to persist. Persistence means that you need to make sure that any dynamic processes will compose well. So if I do one thing and then I do the other and I do the other, I will end up still having an intact thing. And what that means is then that if I'm going to preserve a category and transform it to one to the other, I can say, hey, you and I are both human, right? Socrates is a man, Socrates is mortal. Whatever we define as men are a freaking complicated thing, right? Each of us is complicated. How are we all equivalent? Well, we're not. But there must be some transformation from one person to the other that might change a lot of stuff. But there's something at the core that would be preserved. That's the idea of naturality of a transformation, that there's some really core property that's conserved. And then you can show that if you have closure and the system that you're working with is small enough, like finite. I always work with finite, so I never have to worry about anything. I'm a computer scientist. Everything's discrete in my world. So then you get a bunch of things for free. You get a natural notion of a product, something called a coproduct, which is a way of taking apart product. In category theory, if I told you, hey, we're going to multiply two numbers and get 12. Now invert it. What are the two numbers? Raise your hand when you know. Which two numbers multiply to 12? You return them all. Yeah, that's what category theory does. So you just return them all. So that's called a coproduct. You return them all. That's the natural thing to do. So you also get something really, really interesting, an initial and a final object out of a closed category. The initial thing is like the generator. It's the seed in a generative AI. But the final object is a natural recognizer. It's the thing that can decide whether or not that generator produced something that's reasonable. And that's actually our discriminator in a LLM. But we get other things that just aren't in current AI at all. We get refinability and extensibility. Refinability means that I can take what I currently know and make more distinctions while preserving everything else. That's not the way the training in an LLM works right now. Extensibility means, oh, I've got something new. I have to open up some free slots. Yep. Anyway, so these are all things that you can understand and are some really important things. And once we have more than one category, you start getting really interesting concepts emerge, things that mathematically evoke the feeling that is really overlapping human concepts. Calibration, metaphors, analogies, enrichment, adjunction, duality are the mathematicians' names for things that are like preserving correspondence, blah, blah, blah. Okay, so let's come back to our big, what are we doing in ML, AI? I give you some loss function. I give you some objective, overall objective, and I tell you optimize this, and then you get something, you get a machine that does what you want it to do. So you have a loss and optimization solver in a model architecture. But you also get this. This is called the AI zoo. It's a really unruly zoo. Oh my God. It's like going to an AI conference and every little thing is like 10 additional distinctions off one of these names. There's no unity. Why isn't there any unity? Because some of these problems really are so distinctive in different domains that it's impossible to see the commonalities. Category theory is exactly the right language to think about that. And so if we take the base structure and we build a category theory model, we can build a category theory model that looks really close to just a neural network, in which the model down there is the network. We have an optimizer. We can parameterize our functions in the model exactly the way we parameterize the network. We can parameterize the loss exactly like we do that. We do the learning rate and so on and so forth. But when we do this better, we can suddenly do new things that you can't possibly do, which is you can tear apart this model into pieces, and those pieces will all preserve what the whole system did. And that tearing apart process will be something that's very specific. There will be a way to do it that's universal, provably universal. If you do it some other way, you'll lose stuff. And so here's this whole zoo boiled down into a list of things that are basically tiny differences one to the other, where you can track the change one after the next. And so this is a massive simplification of the parameter space. Oops, shoot. Sorry. So I'm going to try to get you guys here quickly why learn about this. The concept of closure is incredibly important. So what category theory did is they put front and foremost, instead of the idea of emergence, which is the complexity idea, local interactions, something will emerge. Absolutely, something will emerge. So category theory also has local interactions, but they also say, and what happens if we just look at all of those interactions and we just see what happens if we try to close that? So the closure condition means that we try to make sure that you know what happens. So if I have a directed graph, then the transitive closure is the easiest way for me to explain this. I just add all of the arrows. I add all arrows as one-step arrows if you could get there in k-steps. So it just becomes what's called a reachability graph. So you convert a one-step graph into, can I get there? Do you think that's useful? Yeah, that's one of the things that RL agents compute all the time, implicitly. Transitive closure turns out to be the right way to parse sentences too. Huh, interesting. But you can go the opposite direction. This is called the transitive reduction. This is the minimum set of edges you need to represent the system. It's called the skeleton category theory. Both of it, this is cool because it's minimal, but it is throwing away stuff, right? So you don't want to just like stick with this without knowing that this is also part of your domain of interest. And so in category theory, what you do is you start here and you say, hey, I could go this way and I can go this way, and you save all three copies. By saving all three, you suddenly get this ability to transfer back and forth between them. And these transfers allow you to parameterize rewrite rules. So when you have closure over the set of transformations that you have available to you, then you can use these closure conditions to deduce rewrite rules that act like grammar. And these grammar rules, these are freaking powerful. You can tear apart a big neural network potentially and reduce it down to its essential connections. We already know that it's very likely that no matter how big the network is, less than 1 in 1,000 of the connections are going to do anything for you ever. And it's probably less than that. So here's the basic thing. There's universal constructions, which is interesting. You always get to be able to do algebra, and then you get this really important concept that's new. And because there's a new concept that arose in an area, it isn't really familiar. it's an adjunction is a kind of relationship between two things that's sort of like an inverse, but it doesn't have to be a one-to-one. It's just it's exactly this sort of thing like can look up. Can I ignore all of the details of somebody to look up what role they might have played in the past? Sure, if you can, and then if you have the roles, like who's been president of Mexico before. So an adjunction just tries to keep track of the relationship, this looking up back and forth. Obviously, it's a bag in either direction. Who's the set of people that was the president? This person, what offices, political offices might they have held? Those sorts of relationships, they're not one-to-one. What an adjunction does is make sure that if we preserve enough data, it's actually a data preservation condition. We preserve enough data that I can go back and forth. We don't throw away data before it's time. So the most important universal construction for my own research is something that comes out of pullbacks, push-outs, spans, co-spans, blah, 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 blah. So it has to do with patterns of having a module, neural network module, for instance, and another one. Do they come together? Do they converge? Or do they diverge? You guys kind of see the pattern? So converge or diverge. If two things converge, then what happens is it's very likely that distinct values of A and B will produce the same value of C. And from that, you get equivalence classes. Because you get equivalence classes, in order to preserve the right amount of data for it, you have to make sure that every value C is tagged with the pairing of the A and B that made it. Ooh, that sounds like it's really expensive. Yeah, but you can figure out how to reduce it the most. The more interesting one, to me, is the one in which you try to go forward. So I have a common source. I have a generator, and it generated two different outputs. My generative AI was creative. It produced an X and a Y. And so what can you do to understand the two? Well, you basically just do the set difference. That's the intuition. Just do the set difference. If you do the set difference, you'll figure out what's different about the two. Do they really overlap a lot? They're only a little bit, tiny bit difference. And so this construction is called the coproduct, just because one's a product, pairings are products. Then this thing here is you make a disjoint sum. So what does this thing look like? Okay, let's say that I have a generator, which is this little line segment in one dimension, this little line segment in another dimension, and the two of these together make a square. You guys see how that would work? Two different dimensions. So we just take the product of these two, and we get a square. But now I'm going to throw away some stuff in a transform that changes the scale. So the scaling transform. This guy gets extended too. They both get extended by the same transform. These two guys both get extended by the same transform. Now, what we find is that when we pull them together, this rectangle and this rectangle can't make the entirety of the square, but we can extend the entirety of the square and then subtract off what it can make, and you get a partition. These partitions are incredibly interesting and important because it has that set difference feel. If you and I have different concepts, but we actually compare the two and we try to figure out what's different between them, that conversation might result in a new insight. That's the idea with the push out. So how do we partition concepts? Translation actually really helps. Talking to people that speak different languages. The words project out into the world. So if we're embodied, the ability for our embodied mind to come onto a concept, we can look at what words are used for the same circumstances out in the physical world. That's how these little dashed lines are created. So we look at the cases in which the same physical situation resulted in different use of English words, other languages, and you can see by comparison that the concepts must be a little bit different because there isn't a direct one-to-one correspondence, and some languages make more distinctions than others, right? And that the language that makes more distinctions has a richer concept. How can we take advantage of this? Well, it turns out that if I try to make a directed graph respect an order, any order, what it means is that I have signals that I want to push through a directed graph. And as I push the signals through the directed graph, they're going to be penalized on the basis of whether they arrive at the nodes according to some external order, like a reward function. Okay? When we have that, then it turns out that there's a unique way of parceling up the path space. And as we parcel up the path space, we get a disjoint set of paths, and that disjoint set of paths forms a natural basis kind of thing. It's a natural way of doing it. And for directed graphs, we can show that the cycles are always disjoint from the directed part. There's deep theorems in algebraic graph theory that show that those are orthogonal. For undirected graphs, you get these kind of nice partitions. But we can always also go into higher order relationships. This is a simplicial set, and a simplicial set will also decompose. There are fundamental coherence conditions for this kind of decomposition to work. And if you meet them, then you get something almost for free. You get a partition. Now, notice that what I said is that this particular rule, this is if I have a directed graph and I'm penalizing it by an external order, you're always going to get this partition structure as the fundamental universal construction. It's a universal construction for that situation. And it turns out that deep learning resulted in a huge set of new phenomena over standard learning. But around 2018, it was recognized that almost all of these phenomena could be put in a bag of, hey, what if deep learning systems are just memorizing data points and then interpolating? Yeah, memorizing data points and then interpolating. That sounds like it would be bad. Data memorization plus interpolation. That's attention, by the way. Interpolation is attention. When you say attention is all you need, interpolation is all you need. What does it mean to interpolate? It means I have a certain set of things pre-given, stored, and then I look for things that are naturally in between that would be valid. If there's nothing valid in between, it's a signal to make a new partition, make a new cut. When you actually visualize the cuts, you can see that a deep neural network is in fact creating a set of partitions of the input space. Those partitions are real. It means that it switches what it does on the basis of where the input falls. When the input falls in adjacent regions, there is not necessarily any requirement for it to be consistent. So why don't LLMs encode knowledge? Well, they're flexible interpolation machines. And moreover, that's actually the optimal solution. This is the optimal solution to the problem we've posed. So we can't expect it to be better. And so you can get a cool kernel representative theorem and so on and so forth, blah, 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 blah. Okay, does that mean that a lot of the things that people think are true about LLMs aren't true? No, ask me later for the real like complicated story. So I told you that this idea of adjunctions is deep. It creates this idea that two different things might have a core relationship, even though a lot of the details differ. And then what we try to do is try to see how these correspondences work. And when we give them names, it starts getting really interesting. So here's two things that Lever hypothesized, that theories, moving in the opposite direction of a theory, which means that we're going from theory to experiment, gives the semantics for how to make a computation involving a set of objects in a category defined over sets, indexed by the things that you're implementing in your experiment. And the structure on this side, though, of your data should come back and be able to inform you on your theory. Well, that's the science loop. That's cool. Algorithms should be more one-to-one correspondence with data structures. This was hypothesized, and then now we just teach that. Okay, so here's I'm hoping I have time to finish this piece. Here's the big thing for me. Data needs to be invertible. in order to be understandable and interpretable according to the minimal human basis. So what I'm doing here is I'm taking something from a mathematician named Tarski, who was really trying to figure out in the 1950s how to formalize what it is to be a model of something. One thing is a model of another and he found out that what you really need to do is be able to boil down the domain of interest, which was called a domain of discourse, into a set of objects and potentially domain constraints. So objects interact with each other, and the sites in which they're embodied create a set of constraints. And we can attach additional data to each one of our objects using predicates. Predicate is just a function that will take a neuron and add in all of the neuron's attributes. That's actually a type of relation. But there can be other relations, like neurons contain mitochondria, right? And there can be operations and morphisms, like neurons change their dendrites. So I'm going to give us now two things that we would want to be true. I want an evaluation function that would be able to take a domain and a signature, things that help us to characterize what we think is out there. So our objects and this extra data, this really functions, morphisms, dynamics, differential equations, and we boil it down into a set of values that say, hey, is this valid? Is it valid? Is it not valid? Is it valid? Is it not valid? And if I can do that, then maybe I can invert it and then take only the valid stuff, so that if I gave you any object, I can interpret the object in terms of what it can do in the domain. What properties will it have? What operations can it take on? What things would it contain? That's all in this thing S. And if I restrict it to only the valid things, then that's an interpretation. So that's Tarski's idea of an interpretation. And if we just stick with that, then it gives us a well-defined way of thinking about what we've done to data. Data in the modern big data era is a homogenization method in which we try to turn all data into a kind of tokenization so that we can learn from using a set of uniform methodologies. So we creating data maps all of that complicated stuff in the root domain, all of the concepts, all of the relations, all in this stuff, down into rows in a table. And you know that rows in a table will have an index for the row, a row index, and there'll be values, right? So this is that's what it does. Restoring the meaning of the data requires inverting the transform. And in category theory, that's an adjunction. So an adjunction is what we need in order to take the tokenization of our data and map it back out what it might mean in the original domain. There is a universal construction for this. Just tell you that. What will it mean, though, in terms of what we need to do to better represent our data? If we add more structure, it turns out that we need to add a lot more structure. So all of the stuff that I put in there means that we need to do much better bookkeeping. And for the most part, our machine learning methodologies are not capable of handling data with additional bookkeeping. For instance, nested data is a big freaking no-no, even though nesting of data is incredibly important. The only people that are doing this well are biologists. For real. So people that have to deal with actual complexity are at the very forefront of being better with their data. So congrats, everybody who's on that side. In general, we might want to just try to get away with a graph. I said there's a graph with extra stuff. Well, what if it's just a graph? Graphs do a lot, but they're really actually not enough. And the last thing that's eliminated from most of our data projection is the ability to recover the concepts of evidence. Because evidence means that as humans, we are trying to do that data inversion. That is part of what we mean by evidence, that I have some concrete results, some values, and then I use the processes that I know that made the data in order to go backward and try to figure out what it could mean. So the meaning of evidence and the validity of evidence are exactly these backward problems. And the problem now is that evidence has requirements. So if I have evidence and I chain the evidence together, I don't want the evidence chaining to disrupt my truthful conclusions. So if I have evidence from one experiment and evidence from another, and that evidence doesn't agree, right? I can't chain it. So what we need to do is evidence should preserve implication. All of the things that you get from one piece of evidence really should get to another. Otherwise, you have to do some refactoring. Evidence, though, will have equivalence relations. It will be ambiguous with respect to some kinds of this inversion process. But evidence also has algebraic types, and it forms a higher order structure in which we can try to think of how to put all of the evidence together in a way that would be consistent. Now, all of these kinds of things require that we define carefully a partition of the world that the evidence interacts with, because evidence is going to act like an ordering. More evidence, more truthful. Every ordering is going to produce these partition results. Crap. Okay, so where I've been working, yeah, I'm just going to give like a couple more slides. I'll give like a flavor of what I'm doing. What I've been working on now is I've been trying to take the idea of how do we make a minimal model that is big enough that it handles a lot of these problems, but would be relevant for biology. And so we have a big grant that the American government won't give us. They're just not funding it. We're sitting a year and I can't hire anybody to study the problem of how resource constraints affect intelligent beings. And I want to do it from both the AI and the human characterization. This turns out to be a really interesting problem in which the environment can have dynamics. The agent will have its own internal dynamics. And now we model things not as a reward, but as resource exchange. Why resource exchange? Because resources, when they go back and forth, often have implicit equations like you can't make new energy, right? It's really important to keep track of this because these are major constraints on the system. And so following through all of the ideas of how to preserve these relationships induces local gradient-like signals that aren't the same as the gradients we use in gradient descent. And it's being called calibration by the category theory people that work on it. I'm okay with calibration, but the idea is that you want to ensure that the coupling between yourself and the environment is robust. And during that process, you will change your brain. And I believe, I can stop here by saying, I believe one of the most profound things we've done to ourselves as a human experiment is everyone that's regularly using chatbots are adapting exponentially faster to the chatbot than the chatbot is adapting to you. Because chatbots are trained in a way that they cannot serve easily as adaptive systems. It's just an asymmetry. I've got a lot more. There's some really cool stuff with what happens with resource theory and everything. But I never plan talks well. I always think I can go faster than I can. That's the nature of things. So thank you.
Thank you. So we don't have too much time for questions, but we will have time during lunch. So if you have questions for Tim, you can ask them there. So we will have lunch at the same place as yesterday. Okay, just you have to go to the 4:20. Yeah, 40 minutes to it. So be quick. No van a cerrar.